All right, let's dive into something that sounds like it's straight out of a magic show, but it's actually some of the most powerful cryptography out there. We're talking about an idea that's, well, it's completely reshaping our digital world. And it all starts with this one simple, almost impossible-sounding question.
I mean, really think about this for a second. How do you prove you know something secret without, revealing the secret? It feels like a total paradox, right? Normally, if you want to prove you know a password, you type it in. You prove you solve the puzzle by showing the finished puzzle. But what if? What if you could convince someone you know the secret without giving away even a single tiny clue about what that secret is? That's the whole puzzle behind zero-knowledge proofs.
So, here's our game plan. First, we'll really dig into this paradox. Then, we'll meet the cryptographic tool that actually solves it. After that, we'll look at the different security levels, see why this is such a huge deal in the real world, and finally, we'll touch on some of the tricky parts that are still keeping researchers up at night.
Okay, first up, the paradox of proof. Let's get right into the heart of the challenge here. I mean, why is this even a problem we need to solve in the first place?
Well, the thing with a normal, everyday proof is that you almost always end up revealing how you know something. It's like you're not just giving the answer, you're giving away your entire thought process, all the steps, all the data. And that extra information, it just leaks out. In a world that runs on digital security and privacy, that kind of leakage is a massive vulnerability. And that is exactly why we needed a totally new way to prove things.
And that new kind of proof, well, it has a pretty awesome name, the zero-knowledge proof. Think of it as the ultimate secret keeper. It's this incredibly elegant solution that lets you prove something is true without revealing why it's true.
So what exactly is it? At its heart, it's basically a conversation or an interaction between two parties. You've got the prover, that's the one who's trying to prove something, and you've got the verifier, the one who needs convincing. The whole point, the entire magic of the system, is for the prover to convince the verifier, while the verifier learns absolutely nothing other than the fact that, yep, the original statement is true.
Let's just quickly break down those two roles a little more. So the prover is the one holding all the cards, right? They have the secret information, which in crypto speak is called the witness. And the verifier, their job is just to check the prover's claim. But here's the cool part. Their goals aren't the same. The prover just wants to prove their point. The verifier, though, their goal is to learn nothing else. The entire system is built on this really delicate, clever balance.
And this isn't some brand new, shiny idea. The theory actually goes all the way back to the mid-'80s, with this really foundational paper in 1989 from Goldwasser, McCallie, and Rakoff. So what started as a super theoretical academic question has now become like a fundamental tool in modern cryptography. It's been a long journey. Okay, so how does this magic trick actually work? The secret sauce is something called the simulation requirement, and here's the simple way to think about it. Imagine you could create a perfectly believable fake transcript of the conversation between the prover and verifier, a fake one created without ever knowing the secret. If you can do that, well, it means the real conversation couldn't have contained the secret either, because if you can fake it without the secret, then the real one must not reveal the secret. That's it. That's the heart of zero knowledge. Now, it gets a little more interesting here, because it turns out not all zero-knowledge proofs are the same. Their security isn't just an on or off switch. It's more like a spectrum. And where a proof falls on that spectrum all depends on just how perfect that fake conversation we were just talking about really is. So we can kind of group them into three main levels. At the very top, you've got perfect zero knowledge. This is the absolute gold standard. The fake proof and the real one are completely mathematically identical. It's ironclad security. A step down from that is statistical. Now here, they're not perfectly identical, but they are so ridiculously close that telling them apart is practically impossible. And then there's the most common type, computational. This is where a computer, even a supercomputer, just can't tell the difference in any reasonable amount of time. It would literally take more computing power than we have on the planet. Okay, so this is all really cool theory, right? But so what? Why does any of this actually matter? Well, this is the part where ZKPs leap out of the classroom and become a total game changer for, well, everything.
Yeah, so there was this huge breakthrough. It showed that for a massive category of problems, in computer science they're called NP problems, which basically means any problem where the answer is easy to check once you have it, you can create a zero-knowledge proof for it. Just let that sink in. For almost anything from a simple Sudoku puzzle to a mind-bendingly complex logistics problem, you can prove you have the solution without showing any of your work. The implications of that are just staggering.
So where are we actually seeing this stuff in the wild? Well, it's popping up in a few really huge areas. First, it's completely changing how we prove who we are online. Second, it's making it possible to create proofs that don't need any back and forth. And third, it's giving us a way to securely double-check work that other computers have done for us.
All right, first, identification. Just picture logging into any website you use. Right now, you send your password over the internet. That's risky. But with ZKPs, you wouldn't send your password. Instead, you just send a tiny proof that says, hey, I know the right password. The website gets the proof, is totally convinced it's you, and lets you in. But it never, ever, ever sees your password. No way for it to get stolen from their service. It's a total game changer for security.
Okay, next up are these things called non-interactive proofs, or NISKs for short. The name kind of gives it away. Think of the first ZKPs as being like a conversation, a back and forth. NISKs are different. They're more like a sealed, notarized statement. The prover just creates one single package of proof, sends it off, and that's it. Done. This is super important for systems like blockchains or digital signatures, where you can't have a live chat going on. It has to be fire and forget.
And finally, we've got Snarks. Yeah, the name is a total mouthful, don't worry about it, but the idea behind it is just brilliant. Let's say you pay a huge cloud server to do some massive, complex calculation for you. How do you know it didn't make a mistake, or even try to cheat you? Well, with a Snark, the server sends you the answer and a tiny little proof that says, I did the work correctly. So you can verify a calculation that took billions of steps in just a few milliseconds. You never have to redo the work yourself. It's an incredible way to trust computation.
Okay, so as powerful and amazing as all this sounds, ZKPs aren't actual magic. They're incredibly tricky to get right. Implementing them correctly is super, super hard, and there are some hidden traps and complexities that researchers are still trying to figure out. Here's a really weird one, but it's absolutely critical. One zero-knowledge proof by itself, totally secure. Another one run right after, also secure. But, and this is the crazy part, if you try to run a bunch of them at the exact same time in parallel, the whole security model can just break. Information can actually leak between the proofs. And you can imagine what a huge problem that is for any system trying to serve thousands or millions of people all at once.
And that problem right there leads us straight to the cutting edge of ZK research. Right now, cryptographers are working their tails off on things like concurrent ZKPs, ones that are safe to run all at once. They're also trying to reduce what's called round complexity, which is just a fancy way of saying they're trying to make the proofs faster and more efficient. And they're always on the hunt for new, even harder math problems to build this security on top of. It's a field that is moving incredibly fast.
So this is really where it all comes together. So much of our digital lives, our online world, is built on a pretty fragile idea, trust. We just trust that companies won't misuse our passwords. We trust the data we see is correct. But zero-knowledge proofs offer a totally different model, a model where we can verify things for ourselves without having to blindly trust anyone. So I'll leave you with this question to chew on. In a world built on data, what happens? What changes when proof no longer requires trust?